So I wanted to talk about something I learned from Mark Reeder and Ju-Kang Yu about the internal structure of parahoric subgroups, and I'm going to do it in the simplest case. So K will be a local non-Archimedean field, and it'll contain a ring of integers. And I'll choose the maximal ideal will be denoted pi a, and the residue field will be f. It will be a finite field, finite of order q, which is some power of p. And G, as I say, I'm going to do the simplest case. So G will be a split and absolutely simple and simply connected group over K. So some examples are SLN, or the symplectic group, or some more exotic examples like G2 and E8. And so as I say, this is the simplest case to deal with parahoric subgroups and their internal structure. And if you want to eliminate this split condition, you can replace it. If you want to look on my webpage, I have a description of this in the case of general, absolutely simple, and simply connected groups. But the split case is the key case to understand. And this group of k rational points of G is locally compact. And for many reasons, one wants to understand the structure up to conjugacy of the compact open subgroups of G. That's a very complicated issue. But the parahoric subgroups, say P, parahoric it's an example of an open compact subgroup. And all open compact subgroups contain a normal pro-P group. P is this P with finite index. They're basically gigantic pro-P groups with a little bit on top. And in particular, they have natural filtrations. The first step would be the maximal normal pro-P group, and then the Frattini subgroup of that, and then the Frattini subgroup of that, because it's a nilpotent group. And parahorics have particularly nice filtrations that were analyzed by Moy and Prasad. And an example of a parahoric is you take this group, and since it's split, it can be defined over Z. I mean, Chevalier defined these groups over the integers, so you can certainly define it over the ring of integers. And if you define it over the ring of integers, an example of a parahoric subgroup is just the points of G over the ring of integers. That's a maximal. It turns out that's a maximal open compact subgroup. And you might have thought, if you studied real Lie groups, that all the maximal compact subgroups were conjugate. That's what happens in a real Lie group. But that's not true in a p-adic group. And if this group has rank L, in the dimension of a maximal torus, it turns out that there are L plus 1 conjugacy classes of maximal compact subgroups. And they're among the parahorics. Those are the maximal parahoric subgroups. We'll construct representatives for that in this talk. Now, an example of the filtration and the internal structure I want to study is if you take the parahoric, this maximal parahoric, the points over A, then it has a filtration, GA contains, which is normal subgroup, G1 contains G2, contains, et cetera, where these are the points that reduce to 1. This is the kernel of the reduction map to G of A mod pi A. And that's the kernel. And this is the kernel of the reduction map to G mod pi A squared. So these things congruent to 1 mod pi and congruent to 1 mod pi squared. And this quotient is clearly just the group over the residue field. And when you analyze the further quotients, you find that they are just the Lie algebra over the residue field, and they afford the adjoint representation of this group. And that would be what I'd call the internal structure of this maximal parahoric. It has a reductive quotient, which is just the same group over the residue field. And then the various stage of subquotients in this filtration all afford the adjoint representation of that group. And what we're going to try to do is work out the structure of this filtration, which is called the Moy-Prad filtration, for a general parahoric subgroup, and then try to understand what are the reductive quotients and what are the representations that occur in the subquotients of the parahoric. That's what I mean by the internal structure. Now, to do this, to provide representatives of these different maximal compact, and I should say there are 2 to the L plus 1 minus 1 conjugacy classes of parahorics. We'll see how to construct all of them. We're going to build them out of starting from this one and making minor modifications. So let's take the Lie algebra of G. And the Lie algebra of G over A is a lattice, an A lattice that sits inside the Lie algebra of G. Let's maybe call this G of A or something. It's an A lattice in this K vector space G. And one usually analyzes the Lie algebra by using the root decomposition for a maximal torus. So let's choose a maximal torus and contained in a Borel subgroup and contained in G, all defined over A. Again, Chevrolet did this all over the ring of integers, so you can do it over the integers of a local field. And then if you look at this as a representation of the torus, it decomposes into root spaces. And I'll do this for the Lie algebra over A. G of A decomposes, well, you have the Lie algebra of the maximal torus over A. That's where the torus acts trivially. It's its own centralizer. And then you have a sum over the roots of, I'll call them G alpha of A, of one-dimensional, this is a rank 1 A submodule of the so-called root space, G alpha. And these roots are non-zero elements inside of the character group of the torus. Pardon? Yeah, that just means the Lie algebra of S considered as a torus over the ring A. So this is a free A module of rank L. So you can do the decomposition of Lie algebra, and these are each free A modules of rank 1, and they're indexed by a finite subset of the characters of the torus called the roots. Those are definition of the roots. And inside the roots, we have the one-dimensional spaces that occur on the Lie algebra of the Borel, and those are called the positive roots, right? Positive. So they occur in the Lie algebra of the Borel. And when you choose a set of positive roots, that gives you something called a root basis, such that every positive root alpha, so let's call the root basis alpha 1 up to alpha L. There are L of them, where L is the dimension of the torus. And every positive root alpha can be written as a positive linear combination where all the mi of alpha are greater than or equal to 0. These are wonderful properties of root systems. And the remaining roots, the R is the union of the positive roots and the negatives of the positive roots, the negative roots. Now, what we're going to do to define these different parahoric subgroups that are not equal to GA, so to give these extra conjugacy classes, et cetera, is we're going to take the stabilizer of certain other lattices. So the GA stabilizes its own Lie algebra inside of the Lie algebra of G. And we're going to construct other Lie subalgebras by making a very, very simple modification of this. Namely, we're going to keep the same torus. We're going to stay in the same apartment. And what we're going to do is, in these one-dimensional rank A submodules, we're either going to keep the same root space, or we're going to multiply it by pi, or we're going to multiply it by pi inverse. That's it. That's how we're going to construct representatives. Nothing could be simpler. Now, on the other hand, we want them to be Lie subalgebras. So if you multiply the root space associated to alpha by pi, and you multiply, or by pi inverse or something, and you do something with the root space of beta, you have to worry about what you did to the root space of alpha plus beta, because the bracket of G alpha and G beta is in G alpha plus beta. So you have to pay a sort of attention to what's going on inside the root system. And all this is miraculously handled by one root, which is the highest root. So when you have a simple group, like this one, then the Lie algebra is essentially an irreducible representation, so it has the highest weight. And of course, the roots are the weights, so one of them has to be the highest weight. So beta we'll call the highest root. And that has the following property. It's a positive root, and when you write it out as, and I'll write it out like this, mi alpha I equal 1 to L, that the mi's in beta are greater than or equal to the mi's in any other positive root. In particular, they're all positive, because the coefficient of alpha is 1 in alpha. So it has to be higher than that in beta. And they're very important invariants of the root system. In particular, if you take the sum of all of them and you add 1 to it, that's the Coxeter number of G. I'll do an example for you. We'll take a look at the highest root in a simple root system. And we're going to make the other parahorics by studying the root system and this highest root. So let me draw you my favorite root system. This may not work too well, but I'm going to try to draw it anyhow, which is the root system of G2. So G2 has a, let me draw the plane here. It's a root system of rank 2. And one of the simple roots, which is long, I'll draw out here. That's going to be called alpha 1. And the other simple root is short. I'll call that alpha 2. And then you have a root alpha 1 plus alpha 2. And then you have a root alpha 1 plus 2 alpha 2. Sorry, this is supposed to be an alpha 2. And then you have a root alpha 1 plus 3 alpha 2. And then finally, you have a root up here, which is 2 alpha 1 plus 3 alpha 2. And you wouldn't be surprised to see that that's the highest root. And these are the 6 positive roots for G2. And the negative roots are just they're negatives. So I won't draw all of those, but there they are. And so we can calculate the Coxeter number here. You add 1 to 2 plus 3, and you get the Coxeter number of G2, which is 6. OK. Now, we're going to think in the dual space to construct the parahorics. We're going to think in the dual space, which is this vector space, which I'll call V, which is the co-characters of the torus, tensor the real. So that's this is the character group of the torus, right? Tensor R, and I've denoted inside of that two-dimensional real vector space. These are the vectors which are the positive roots, and the alpha 1 and alpha 2 are my 2 simple roots. All right. So these give linear functionals on this space, and we're going to consider not just linear functionals, but, and this is the wonderful idea of Bruja and Titz, affine linear functionals. So to each root, alpha in R, and to each integer, n in Z, we're going to consider psi, which is defined by alpha plus n, as a linear functional, an affine linear functional from V to R, by which I mean it takes a vector, it takes a point x here into alpha of x, that's the linear map, plus this integer n. So it's affine linear. And we're going to consider all the hyperplanes that we get in this dual space where these affine linear functionals are 0. So let's write down a few of those hyperplanes. This is going to be my next incredible attempt to draw something. Now, if you actually try to draw these hyperplanes, you get into an incredible mess. So I'm just going to draw a few of them for you. First of all, where does this simple root vanish? Well, that's the vertical axis, right? That's the thing's orthogonal to that. So here's the hyperplane right here. Now, I better use another color, it occurs to me. Let's try this. Here's the hyperplane where alpha 2 is equal to 0. Let's draw the hyperplane where alpha 1 is equal to 0. Well, that occurs at a 30-degree angle here. How about the hyperplane where beta is equal to 0? Well, beta is the vertical, so that's this hyperplane here. But those are actual just linear functionals. Suppose I took the affine linear functional where beta was equal to 1. Well, beta is equal to 1 would be somewhere up here. And beta is equal to 2 would be somewhere up here. And for example, if you're interested in where the co-roots are, the co-root associated to beta, if you know co-roots, here's the point beta check, because beta check has inner product 2 with beta, and it has inner product 0 with alpha 2. OK, when you start drawing all these hyperplanes, the beautiful thing is that it tessellates the space V into simplices. And in this case, the simplices are 30, 60, 90-degree right triangles for G2. This is a fundamental thing. And we define the basic affine roots, the ones that I'm going to use to define the parahorics. Basic affine roots. They're going to be L plus 1 of them. C0 is going to be the root minus beta plus 1. So that's the new thing, where you add, you use the highest root, you take minus it, which is the lowest root of the adjoint representation, and then you add the integer 1. And the others, V1 is just alpha 1. They're just linear maps. VL is alpha L. So there are L plus 1 basic affine roots. There are other choices. And if you take a look at the region in this dual space called C, the region where all the basic affine roots are greater than or equal to 0, you get the closure of what's called the fundamental alcove. And that's right here. You see, if alpha 1 is bigger than 0, you're in this half space. If alpha 2 is bigger than 0, you're in this half space. And if C0 is bigger than 0, this is the hyperplane where C0 is equal to 0, because the C0 is the root minus beta plus 1. So if beta is equal to 1, and where it's positive is down here. So this is the fundamental alcove. And it turns out that this gives a fundamental domain for the Coxeter group that's obtained by reflections in all of these affine hyperplanes. That's a beautiful theorem which you can find in Bourbaki. OK, so this is the alcove. Now we're going to define parahoric subgroups associated to each facet of that alcove. So what's a facet of that alcove? Let's see if I've missed anything. So, oh, yeah, one more thing, which I almost blew. Look at this. If you add up all of the affine roots and you let M0 be 1, and then you take the sum of Mi psi I, that's equal to just the affine linear functional 1. Because when you take the Mi of these, they add up to beta. You multiply this by 1, it cancels the beta, you just get the constant function 1. So these psi I can't all be 0 on this alcove, because the sum of them with these coefficients is equal to 1. So on the other hand, you can have facets of the alcove where some of the psi I are equal to 0. For example, the open alcove would be where none of the psi I are equal to 0. And you have 7 facets here. You have the 3 different vertices. That's where 2 of the psi I are 0. And then you have the 3 different edges. That's where 1 of the psi I's are 0. And then you have the place where none of them are. So how many facets do we get? Well, we get exactly 2 to the L plus 1 minus 1 facets, because you get a facet by choosing a non-empty subset of the set 0 up to L, which has L plus 1 things. So they're exactly 2 to the L plus 1 minus 1 non-empty subsets. And you insist that psi I is equal to 0 for I not in your set sigma. OK? So the vertices would be where these non-empty subsets consist of one simple affine root. For example, this vertex here, the vertex 0, is where psi 0 is not 0, but psi 1 and psi 2 are both equal to 0. OK, now what's nice, and we're going to associate a parahoric to each facet. Now what's even nicer is you can associate a canonical point to each facet. And I think this certainly simplified the situation for me. Namely, the vertices, it's clear how you associate an obvious point. But if I wanted to appoint a point for each facet, I should just take the barycenter of the facet. So to each facet f, you associate the point x, which is its barycenter, which just means it's the point where the psi I, where the psi I of x are all equal for x, for I in your set sigma. So you just, now that's not the actual barycenter because you have different weights here. You see, you can figure out what they have to be equal to by taking this law. I mean, you have to have the sum over sigma of the subset, I won't write sigma over sigma, of mi times the value of psi I of x has to be equal to 1. And these things have to be constant, so they have to be equal to 1 over the sum of the mi in that subset. Okay? So for example, what are they equal to if you take the barycenter of the chamber in there? Well, all of them are non-equal. And on the other hand, we have that the sum of the mi psi I is equal to 1. And it turns out that in this case, they are all equal to all the psi I of x turn out to be equal to 1 over h. You'll find out where that's the Coxeter number. And in general, you get various. So here it turns out that what do we have? At this point, we have that, psi 0 is equal to 1, and the others. At this point, you'll find that psi, which is the one that non-vanishes on it, psi 1 is equal to a half, it turns out. And at this point, you'll find out that psi 2 is equal to a third, because that's what the m's are, right? The m's are 2 and 3. And so the barycenters have rational coordinates in some sense. And here, the psi i's are equal to a sixth. OK? I think that's all the simplicial algebra that I need. And you can imagine doing this in general. Now, let's just make one more observation. Inside of C, because forget about the highest root, all of these roots take non-negative values, right? And therefore, all positive roots, which are positive combinations of these, take negative values. So in C, alpha of x is certainly greater than or equal to 0 for alpha in R+. But I claim they're also less than or equal to 1, because none of the roots are bigger, take a bigger value than the value of beta, and 1 minus beta has to be positive, so beta has to take a value less than or equal to 1. So for any x that's in this fundamental region, all of the positive roots take values between 0 and 1, and all of the negative roots, therefore, take values between -1 and 0. OK, let's put this up, because we'll need this. Whoa, let's pull this down. OK, now I think I can define the parahorics. And anything else? No. Here we go. So to each x, which is a barycenter of a facet of C, I'm going to define a lattice in the Lie algebra, Gx in G, an A lattice, using the root space decomposition. So it's going to start out with the same torus, Lie of S over A. You don't change that at all. And then I have to put in root spaces. So I'm going to define direct sum over alpha in R, pi to the n alpha times G alpha of A. So I'm going to modify these one-dimensional A modules by multiplying by some power of the uniformizing parameter. Which power? So n alpha is the smallest integer such that alpha of x, the point x, the barycenter x, plus n alpha is greater than or equal to 0. OK, now let's make some observations. If alpha is a positive root, then alpha of x lies between 0 and 1. So therefore, this n alpha is either equal to 0 or minus 1. If alpha of x is equal to 1, then you can take n alpha to be minus 1. And otherwise, you have to take n alpha to be 0. So consequently, and also if alpha is a negative integer, n alpha is either equal to 0 or 1. And you only get 1 if they're all negative. OK, so we've just made a very minor modification of these different root spaces. And then you can do the same in a group if you want to. And you check, using the properties of adding roots, et cetera, that this is a sub-Lie algebra. And it corresponds to a Lie group over A. And that Lie group is Gx, or Gk of x, the corresponding open compact in G of k. You can define that, if you like, by taking the torus, spanned by the torus, and the root groups u, I don't know, maybe u alpha of pi to the n alpha. So this is a subgroup of the root group, but you could also take it as the group with Lie algebra this. That's the definition. So notice that we haven't modified much, but the modification, which power of pi you choose here, depends on where you are in the fundamental alcove. So let's do an example. Let's do one example. So if we take x to be the barycenter of C, of the interior of C, then when then psi I of x is 1 over h for all I, for all the basic roots. So we find that alpha I of x is 1 over h, and we find that beta of x is 1 minus 1 over h. And that's the largest value. So therefore, all the positive roots take values between 0 and 1 inside this barycenter. And consequently, all the negative roots for alpha greater than 0, and all the negative roots take values between minus 1 and 0. And consequently, for all the positive roots, n alpha is 0, because it's already greater than or equal to 0. So you can take n alpha equals 0. You can't take n alpha equal to minus 1, because then it wouldn't be bigger than 0. But for all the negative roots, n alpha, you have to take n alpha to be 1, right? Because you want to make this value plus n alpha bigger than 0. And consequently, what you've done for the barycenter of the interior is you've got the Lie algebra of S over A plus the direct sum over the positive roots of the same root space you had for the A-valued points of the group, and then plus the sum over the negative roots, pi times G alpha of A. And that's called an Iwahori subalgebra. But in general, when you don't go to the interior, some of these become 0, some of those become minus 1, some become 0, some become 1. It's quite a complicated story. All right, well, if we did this, why don't we define the filtration that Moy and Prasad defined? You see, the value of this, suppose this has denominator d. Namely, all the things that are non-zero on it take the value 1 over d. In here, they all took the value, d was h. But in general, d is less than or equal to h, because it is the sum over that subset of the mi's. OK, well, then this plus this is some rational number with denominator d, because if this is true, then that's true for all the alpha I of x are equal to 1 over d. And alpha is an integral combination of the alpha I. So you get this thing is some rational number with denominator d, and this is an integer, so you get something with denominator d. So we could define a filtration of this, and that's what the Moy-Prad filtration is. X, let's call this subalgebra A over D, where A over D is some rational number greater than or equal to 0. We take the following. Inside of the Lie algebra, we take pi to the m times the Lie algebra of S over A. And then we take the direct sum of the root spaces pi to the m alpha g alpha of A, where m is greater than or equal to A over D. And for small values of A, you can take m equals 0. And m alpha plus alpha of x is greater than or equal to A over D. And these are the smallest integers with these properties. So obviously, as you let A over D get bigger, you have to take a bigger value of m alpha to get it bigger than A over D at certain points. So this is a submodule of this, and clearly this is a submodule of this. And you can check that this is a sub-Lie algebra, and so you get a nice filtration, and you can do the same thing with groups, and that's the Moy-Prad filtration. Gk of x contains, as a normal subgroup, gk of x 1 over d contains gk of x 2 over d. And if you do this for the point which is the origin, and I should have said that's a particularly nice point, and the parahoric you get here is the parahoric g of a. And d is equal to 1. At hyperspecial points, you'll find the denominator is 1. And so then the filtration is just by the reduction mod pi. But in general, this refines the filtration that you get by reducing mod pi and mod pi squared. So far, so good? That's the definition. OK, now what's the theorem? So this was, as I said, all done, and a beautiful work of Moy and Prasad. And what Reader and you looked at, which is a perfectly reasonable question to consider, is what is the structure of, let's try, well, let's do it in the Lie algebra setting, gx a over d modulo the next step, gx a plus 1 over d. Right. Namely, these A modules may be difficult to understand, but maybe if we divide out by the next one, we can figure out what's in this. OK? Now, this is completely elementary, but it's extremely cool. I claim, let's do the case where A over D is between 0 and 1. So there's no change in the Lie algebra of S. This m can be taken to be 0, because it's right? Yeah, whoops. Wait a minute. M to be 1, but I don't want m to be 1. Maybe I made a mistake, terrible mistake here. M is bigger than or equal to A over D. No, that can't be right. No. It must be m plus 1 is bigger than or equal to A over D. Let's try that. No, that doesn't work? Well, let's see what I want here. I want this to go up when A over D. It's not this. It's not this. Yeah, I think this is right, actually. You see, when A over D gets to 1,
like in the pluripotent radical of evil, pluripotent radical for the evil 4, you're going to jump
immediately. Yeah. Sorry, you're right. So I want m to be, got it. I want m to be greater than A over D. All right.
No, you just want to take A over D and round it up to the nearest integer.
What did I have down? What I had?
I think it was fine before.
It was fine before?
Yeah, so n equals 1.
Oh, it gives you, thank you, thank you, thank you. Good. But you see, when A over D is, let's go bigger than, yeah, you're right. I want it bigger than 1 over D. That's it. So I don't have any change in S. Namely, S has already been, it's the same value of M for all the, yeah, for A over D bigger than 0. That's it. Because if I start off at 1 over D, it's the same. M is 1. And going to 2 over D, it's still 1. So the Lie algebra of S doesn't change the power there. Good, 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 good. So I just get a sum over the root spaces where this M becomes 1 larger because I've gone to A over D plus 1. And which root spaces would I get? So this would be the sum over the certain root spaces alpha, certain roots, of pi to the M alpha G alpha divided by pi to the M alpha plus 1. Because to get bigger than this, I've only added something which is possibly less than 1. So I have to go 1 more. So this is just like a one-dimensional vector space over my residue field, right? And which alpha would I get? Well, I get the alpha where I would have to increase this integer to get bigger than A over D plus 1. Namely, I get the alpha where alpha of x was equal to A over D plus some integer. And the certain roots, those alpha where alpha of x plus, let's see if I can write this down properly, M alpha or N alpha, did I call it N alpha, is equal to A over D for some integer n alpha, right? Because if it were equal to A over D, N alpha would work for this, but I'd have to take a larger power to get it into the next stage of the filtration. So you get a direct sum of certain root spaces, and it's over the alphas with this property. Now let's take a look at what those alpha really are, because this is the key observation in their argument. So first of all, it's an F vector space. That's always a good thing to have. And let's multiply this expression by D. So that means that alpha of dx, you multiply, to evaluate a linear function, you can multiply it by the point, plus D times N alpha is equal to A for some integer N alpha. Or in other words, here we use some number theory so I feel comfortable, that alpha of dx, which is just the inner product of the root alpha with the element dx in the dual space, is congruent to A modulo D. Right? Because if it's congruent to A modulo D, that means the difference is D times an integer. That's it. So I now know which roots I have. I have a sum of one-dimensional vector spaces taken over the roots with this property. Now, that's not just as a vector space, if you think of it. That's as a representation of the torus over a finite field. So this gx, A over D, mod gx, A plus 1 over D, has now been identified as a representation of the torus over the finite field, where you get one-dimensional spaces corresponding to exactly these characters alpha, because the characters are characters of the torus over the finite field. Well, we're getting there. We're getting there. So far, we've just got it as the torus, because we've identified the root spaces. Now, what representation of the torus is that? Well, consider the following. You see, this alpha dx is an integer for all alpha. And that means that this multiple of our point, which was a rational point in this building, here I've multiplied it by 2 and I've gotten it up to here, or here I've multiplied it by 3 and I've gotten it up to there, is actually a co-character of the adjoint torus, because the adjoint torus has its character group spanned by the roots. And if you have a linear function that's integral on all the roots, it's a co-character of the torus. So dx is a co-character, namely a homomorphism from the multiplicative group to the adjoint torus, S modulo the center. And the adjoint torus is certainly a subgroup of the adjoint group, right? And the adjoint group acts on the group by conjugation. So my point in this fundamental alcove here, if I multiply it by its denominator, D, gives me a co-character with values in the automorphism group of the group. And I can decompose the Lie algebra for that co-character, and I get a bunch of eigenspaces. Well, that's not quite what I want. You see, if I didn't have this modulo D and I just said alpha dx is equal to A, that would say it was in the A eigenspace, that the root space alpha was in the A eigenspace for this co-character acting on the Lie algebra. What does this mean? Congruent to A mod B. That says that if you restrict this co-character to the subgroup of d-th roots of unity inside of GM, which is the d-torsion subgroup, that maps to the automorphism group of the Lie algebra. And so it gives a decomposition of the Lie algebra for that action. And what is that decomposition group like? Well, a torus action gives you a Z decomposition of the Lie algebra. A mu D action gives you a decomposition of the Lie algebra as a direct sum over the character group of mu D, which is Z mod D. Eigenspaces for the mu D action. And if you want to know which is this eigenspace, it's the eigenspace where zeta acts by zeta to the A. Or equivalently, it's the direct sum of the root spaces where the inner product of dx with alpha is congruent to A mod D. And so what we've shown, take this eigenspace decomposition over F, what we've shown is that for A between 0 and 1, that this quotient is isomorphic as a representation of the torus to this eigenspace GA in the Lie algebra for this mu D action. Okay? And you get an action from the point in the building. Now that looks completely, and that's just as a representation of S. We have an isomorphism as a representation of our torus over F. Now, as has been observed, this is just the beginning of the story. Once Reader and you noticed that the characters of the torus mapped up, they thought, well, this is actually, each eigenspace is a representation of a group that Winberg calls G0, which is the centralizer of the mu D action. So that has the Lie algebra is equal to G0. And each one of these eigenspaces is a representation of this reductive group. The fixed points of a mu D action are connected reductive in this case. So each one of these eigenspaces is a representation of this. And as you observed, each one of these quotient spaces is actually as a representation of Gx modulo the first step of the filtration, Gx 1 over D, which is what's called the reductive quotient over F. And what Reader and you prove, not surprisingly, is that this reductive quotient over F is isomorphic to this fixed space of the mu D action. You prove that by using the fact that the groups have the exact same root data. And, moreover, that these representations are not just isomorphic as representations of the torus, but that this subquotient as a representation of the first step of the filtration, the reductive quotient, is isomorphic to this eigenspace in the Lie algebra as a representation for this fixed group. That's their theorem. Now, you might say, this is kind of easy. And as many dictionaries go, it is pretty easy. I mean, the actual conversion of this proof from a representation of the torus to the representation of the group is very clever, but if I had another half an hour, I could do it. It's not impossible. And so what do you get out of this? It's just the translation of this identification of root spaces that lie in the subquotient with the identification of root spaces that lie in the eigenspace. What do you get? Well, you get quite a lot. And the reason is that these decompositions of a Lie algebra for a mu d action were studied extensively by Wimberg and his school, people like Victor Katz and Eliashvili and Panushev. Independent of parahoric subgroups, they didn't care about parahoric subgroups. They studied these mu d actions in the 1970s and showed they had a beautiful invariant theory, completely analogous to what Chevalley proved for the action of a Lie group on its Lie algebra. So what they proved, and Chevalley, remember, proved the theorem that if you took the symmetric algebra on the Lie algebra and you took the invariance under the Lie group, it's a polynomial ring in L generators. I mean, the symmetric algebra is a polynomial ring, but why should the invariance be a polynomial ring? In other words, in the language of geometric invariant theory, the geometric quotient of the Lie algebra by the Lie group is isomorphic to affine space of dimension L. And what Wimberg and his colleagues proved is the same thing happens if you take a mu d action and you take the action of G0 in any of these eigenspaces. So in particular on the one eigenspace. So Wimberg's theorem is that if you take G of 1 and you take the adjoint quotient by G of 0 is affine space. And the proof is very similar. Chevalley shows this by showing that this is isomorphic to the symmetric algebra on the torus, maximal torus, invariance under the Weil group, and then appeals to the fact that the Weil group acts via it's a reflection group on the reflection representation, and invariant ring is polynomial. In Wimberg's case, you define Cartan subalgebras, et cetera, and you get complex reflection groups, but the invariant theory is exactly the same, so polynomial invariance. And what that allows, this dictionary that Reader and you have then allows them to show that the action of LF on these subquotients of the Moy-Prad filtration are also polynomial invariants. And that's a theorem, if you think of it, that's very much like the structure of parabolic subgroups. It's a little weaker. For parabolic subgroups, an important theorem is that you have the action of the Levy quotient on the various steps of the unipotent radical. And the theorem is, which you can see find in all the books, that action has an open, dense orbit over an algebraically closed field. That's how you get generic characters and things like that. And so that when you have an open, dense orbit, you have the invariance reduced to the constants. So that's the simplest kind of invariant theory. These actions don't always have an open, dense orbit. In fact, they rarely do. But at least the invariant theory is very simple. It's polynomial. And that allows Reader and you to discover which orbits of LF on this space are semi-stable and stable in the sense of Mumford's geometric invariant theory. If the invariant theory were more complicated, the identification of semi-stable and stable orbits is a nightmare. And so that allows them to construct some wonderful representations. So I'll just give you an example to show you how beautiful these representations are, at least to me. At least to me. Let me see if I can do an example here. Let's go back to G2. So for example, you can ask, and they answer this question, when does, so you have some parahoric subgroup, Gx contains Gx 1 over d, contains Gx 2 over d. So let's call this representation V1, and let's call this reductive quotient LF. So part of this theory says that the LF invariants on V1 are polynomial. You can ask, when does LF have stable orbits on V1 dual, on the dual space, Hom from V1 to F. And the answer is beautiful. It's for the parahorics which correspond to regular elliptic classes in the Weil group. So I won't do this correspondence, but to a regular elliptic class in the Weil group, you can correspond to certain parahoric. You don't get too many of them. So for example, in E8, and let's do G is equal to E8, there are 511 distinct conjugacy classes of parahoric subgroups. Right? This is 2 to the 9th minus 1. Right? And it turns out there are exactly 12 of them have correspond to regular elliptic classes in the Weil group. You always get the Iwahori, because the Iwahori corresponds to the Coxeter class in the Weil group. But in other Weil groups, there can be, other than AN, there are other regular elliptic classes, and gives you some other interesting parahorics. Now, if you do have a stable vector, if you have a stable vector in V1 dual, then that gives you a map, you see, from Gx 1 over D. It has a quotient map to V. And then your stable vector, let's call that lambda, maps you to F. And then you can choose an additive character of F, a non-trivial additive character to C star. And you get an interesting one-dimensional representation of this pro-unipotent radical. And Reader and you show that if you take the induced representation of this one-dimensional representation, that's a finite direct sum, finite length, and a direct sum of supercuspidals. Of supercuspidals of depth 1 over D, where D is the denominator of X. So it's amazing that you can take such a simple, this is a one-dimensional representation of a group, but it has to come from an element in the dual space which is in a stable orbit. And that's what gives you the finite length property. And they construct a lot of interesting representations this way. So Reader had previously done the case where this was the Iwahori, and D was H. And these stable vectors are exactly what we called affine generic characters of the pro-unipotent radical. And these induced representations were what he called simple supercuspidal representations. But they exist for other parahorics, which correspond to regular elliptic classes. And as I say, just to show you how rich this is, I'll do it to you for G2. For G2, the regular elliptic classes in the Weil groups have order 2, 3, and 6. D is equal to 2, 3, and 6, the orders of the regular elliptic classes. And this is the Coxeter class, and this is the square of the Coxeter class, and this is the cube of the Coxeter class. Okay? Now, let's go back to the little right triangle I had here. Okay? So, which parahorics correspond to these regular elliptic classes? Well, the Coxeter class corresponds to this X. This is the X for 6. That's the Iwahori, right? And what about 2 and 3? Well, there's only one facet where the denominator of the barycenter is 2. And this is the one where X is of order 2. But there are 2 barycenters where the denominator is 3. This thing has denominator 3, and also the barycenter of this facet has denominator 3. Now, if you take this parahoric, that's a maximal parahoric, and people had studied that. And that turns out not to be interesting, because here Gx, the first quotient, is SL3 of F. That's Gx 1/3. And then the next quotient just gives you the standard representation of SL3F on the standard representation. And that has an open dense orbit, so there's certainly no interesting polynomial invariance, and that's not, no stable orbits. So it has to be the other one. The other one is somewhere around here, X3. And here, you find when you take the parahoric and you calculate its reductive quotient, you get the group GL2 of F. Right? And then that's GX 1/3. And then GX 2/3. You get a representation here which has dimension 5. And it's the representation of GL2F, which I'll write down as follows. You take the symmetric cube of F squared, and you tensor it with the inverse of the determinant. So that's a 4-dimensional representation. And you take the direct sum of that with the inverse of the determinant, which is a 1-dimensional representation. And that representation turns out to have a polynomial ring of invariance, a beautiful polynomial ring of invariance. And the polynomial ring has dimension 1. It's generated by an invariant of degree 6. Polynomial invariant. And that at least this, I'm assuming, by the way, that the p is bigger than 3 in this case. There are some cool things that happen at p equal 2 and 3. And we've been really trying to do this theory in all characteristics, but I'll do p greater than 3 here. Then this representation is irreducible. This is irreducible, so it's the direct sum of 2 irreducibles. And the polynomial invariant looks like this. If you take a vector in this representation and you write it as a binary cubic form, so that's a qxy, and a vector z, which is just in the field, because this is a 1-dimensional representation on the field, then the degree polynomial, the degree 6 polynomial invariant is it maps to the discriminant of q, which is a quartic semi-invariant. It's invariant under SL2, but not GL2, times z squared. And this is of degree 4, and that's of degree 2, and that's the unique polynomial invariant of degree 6, which generates the ring of polynomial invariants. And the stable orbits are where this polynomial invariant is non-zero. So that means that this binary cubic form is non-degenerate, has non-degenerate discriminant, and z is non-zero. And from those stable orbits, if you take the induced representation in this sense, you get a sum of interesting supercuspidal representations of depth 1/3. And I should say that Reader and you have also analyzed the case where you don't just use V1, but you use the higher depth, and they analyze when you have, they've made a classification of when you have semi-stable orbits, when there are semi-simple elements in those representations, and so they have a very much better understanding of what depth supercuspidal representations can occur. Thank you.
So you took only Barycenters, but suppose you take other forms?
You don't get anything more interesting. Namely, all the semi-stable and stable vectors occur at Barycenters.
Oh,
namely, Moy and Prasad have a much more general filtration where they have filtration for any point in this. And it becomes, you know, it's a slightly different filtration. Same reductive quotient, but different steps in the pro-unipotent radical. But all the interest comes from the Barycenter. That's part of Winberg's theory, too. So,
what we needed other forms.
exactly. But in this case, I think you can just get away. It's somehow a miracle that the case that you know the most about is the case you need to know. Isn't that right, JK? Is that fair to say? OK. That may be a little too strong. But the Moy-Prad filtration takes any point in the building. It helped me a little bit to have these 1 over D and 2 over D and not R and R plus.
But, in the proofs, we needed to move around.
Exactly. Maybe this will encourage people to read their beautiful papers, and that it's more involved than this, much more involved.
Do you know the Langlands parameters for these?
Yes. Reader and independently Calatha have worked out the Langlands parameters. In the case, you have to make some hypothesis on P. I think they know the Langlands parameters, Tom, in the case where, say, P doesn't divide the order of the Weil group, something like that. And it's exactly the same as what Reader found for simple supercuspidals, namely the image of, so you have a parameter, it's just a homomorphism, really, of the Galois group of the separable closure. You don't need, there's no unipotent part, there's no Weil part, right, into the dual group. And so this has a filtration by tame inertia, right, and then there's wild inertia. So wild inertia goes into regular elements of order P in the torus. and consequently the whole parameter goes into the normalizer of the torus. And the quotient of tame inertia, so this goes into the normalizer of the torus. And if you map it to the normalizer, if you map it into the quotient of the normalizer of the dual torus by the torus, which is isomorphic, or maybe anti-isomorphic, Stephen, I don't want to say anything wrong, to the Weil group, right? Then the image of tame inertia mod wild inertia maps to the conjugacy class of this regular elliptic element. So previously it had gone to the Coxeter element, now it goes to this regular elliptic element. And then Frobenius maps to something in the normalizer which tells you in Mark's thinking which conjugacy class of Cartan subalgebra you use in the Windberg theory. I won't go into that, but they have quite an elaborate description of the Langlands parameter. And it's basically using the fact that the Weil group of the group and the Weil group of the dual group are isomorphic. And it gets much more interesting when you have a prime that divides the order of the Weil group, because then the image of the parameter is not contained in the normalizer of the torus, but the representation has been constructed, so you better find something. And Reader and I played around with that a little bit.